let me introduce you to another factor that affects weather. Everybody heard of latitude and longitude? Okay, this is just the way I remember which way they work. Notice I've got a picture of a ladder on the screen. Notice the rungs of the ladder go this way. That's how I remember latitude is like the rungs on a ladder. That's latitude on the earth. And then we have the other thing called longitude. Longitude goes around the earth this way. It goes the long way around, north to south. So that's how my brain remembers long for longitude. Because if I back up, check this out, right? Latitude. Some of the rings are shorter because they're up near the top or bottom. Whereas guess what? With longitude, the same long path all the globe. So we got latitude, we got longitude. Here's how this all plays together. There's this thing called Coriolis. And I'm going to walk you through this. If you were standing on the North Pole and you stood there for one full day, the actual distance that you would travel would be pretty tiny. I mean, yeah, you'd go around a circle, but your actual path around the circle is almost nothing. Whereas for you, George, down on the equator, in one full day, you're going around a much bigger circle. So you're actually traveling a farther distance in that same 24-hour period. So at the North Pole, basically you're standing still, and down on the equator, you're going really fast and a long way in a 24-hour day. So that latitude actually determines how fast you are going around on the Earth. In essence, you got 0 at the North and South poles, and as you get closer to the equator, you're going faster and faster and faster and faster and faster. Now think about the air, the atmosphere on this ball we call the Earth.
Yeah, I thought
At
this whole discussion of the Coriolis effect and what you're talking about right now, I thought it was rather fascinating. Something that I had never really considered the way we are in this class.
So how have you considered Coriolis before?
I mean, I had considered that, that I guess I knew in the back of my head that, we're moving rather fast on the Earth in a circle. But
Yep.
as far as how that affects the weather or even launching rockets or anything
Yeah.
like that, I had never considered, you have to calculate for moving, whenever you're launching something from one spot to another, you have to figure the Coriolis effect into it in order to launch it, or, things, or how that affects the weather, or, it's just the whole thing was like, wow, that's pretty amazing, pretty interesting, to think about.
It is. And in fact, in my engineering classes, an example they gave us was that uh, early on, around the time frame of World War I, when they started building these large battleships known as dreadnoughts with these huge cannons, okay, that were able to launch these massive shells that would fly for miles and miles and miles, meaning they'd have a lot of time in the air. When they first started, doing the basic calculations, they just said, okay, we'll do basic projectile motion. Again, something I cover in physics. And the equations are pretty simple. And they kept missing the target. And they kept checking their math. And they kept missing the target. And they'd correct their math, check their math. They kept missing the target. And then finally, like you, Joe, they went, oh, we have to account for the fact that this projectile is in the air long enough for the Earth to rotate underneath it. Kind of like the missile example in the textbook. And you know what? Once they threw that term back into the equation and accounted for it, boom, hit the target every time.
Keep saying physics only works in a vacuum, man.
And I've got a great video for that later when we get to that lesson. Joe, that encourages me that, but it's like the light went on. That's good. All right. I'm not going to watch this video. I had you guys watch it. It does a great job of demoing, so I'm going to move on past this one. Okay. Now, there's another thing that's going on, and it's driven by the fact that land, basically dirt, heats and cools at a different rate than water does. So let me walk you through this picture. Daytime, sun shining, it heats up the land. Warm air rises, okay, and then it cools and comes back down. Moves out over the ocean. And so you see that during the day, we get what's known as a sea breeze. If you've been to the beach, you notice that the breeze during the day tends to be blowing in your face from the water. And then the bottom picture, it's exactly the opposite. Land cools faster than water.
Yeah, that was another light bulb that went off in my head, because I always wondered how people were able to predict that at a certain time in the morning it was going to be windier, and then at night the same thing. And so then when I was talking about the differentiation between the heating of the earth versus the heating of the water and how it contrasts at certain times of the day, then you can basically predict when you're going to have a particular type of breeze. And I thought that was pretty cool.
Yeah. Now, here's what we've got going on. We've got convection, changing air temperature. Warm air rises, cool air falls. We've got the Coriolis effect, the earth spinning. And then we've got the local winds, the land breeze versus sea breeze. And all of that pulls together. And I like this picture. It kind of brings all those pieces together. And I'm going to leave it up and let you look at this for a little bit. So you got rising and cooling air. You've got Coriolis. Okay. Then you got land and sea breeze. Okay. So all of this interacting is what creates weather. And to me, the basic principles that make it all happen are fairly simple. Now, the way they interact and play out, that can be very, very complex. But the basic principles are very, very simple.